Okay, and we're going to move on to chapter 6. And we're probably going to have another test. Probably not next Thursday, but the following Tuesday. That seems like about where we're at. So just kind of put that on our tentative to-do list. But in chapter 6, we are going to talk about something else called random variables and discrete probability distribution. So let's define what a random variable is first. Okay. So a random variable is a function or rule that assigns a number to each outcome of an experiment. And I want you to think about that. Like, for example, when I did this little experiment with my wife, what I was concerned with was the number of females that we got out of this deal, right? So if you assign a random variable, it would have been 0 for that outcome, 1, 1, and 2, right? That's the random variable. So oftentimes I don't care about all the individual paths, you know what I'm saying? I'm concerned with some outcome, some random variable. It's a numerical event. So instead of talking about coin flipping event, if I flip a coin 10 times, I want to know the number of times I come up with tails. That's the random variable, right? If I play 10 games, I want to know the number of wins I get. That's the random variable. The thing I'm interested in studying is the random variable. I don't care about all the combinations. It's nice to know those, but I care about something like the outcome, the number of outcomes. So we're going to talk about two different types of random variables. And the first one is a discrete random variable. And the discrete random variable means it's countable. Continuous means uncountable. So let me give you an example. If Mark and I played a game, Mark, give me a number between 1 and 10. 7, between 7 and 10, Mark. Between 7 and 10. Between 7 and 8. Between 7 and 7.5. Between 7 and 7.2. Between 7 and 7.1. Okay, so how long can you and I play this game? Yeah, forever. We don't run out of numbers, right? Because if we're talking about real numbers, we can always slice them thinner and thinner, yes? So things like that are attracted by real numbers, we call those continuous, like time, for example, right? We can slice time thinner and thinner. We can talk about nanoseconds, right? So those are continuous. Time, even things like your height, your weight, you're probably not exactly 73 inches tall. You're probably 72.97341 inches tall. So any kind of real number is continuous because there's an infinite amount of values that can take on. Does that make sense? Like how long did it take you to walk over here? There's an infinite amount of values that can take on. Those are called continuous random variables. Now discrete means countable, okay? How many times does a coin come up tails when I flip it 10 times? That's countable, 0 through 10. How many children do you have? That's countable, 0 through Duggerland, whatever, 17, whatever they have, okay? How many TVs do you have in your house? That is countable. That's a discrete random variable. So if you think about it, anything that is countable, like an integer, is called a discrete random variable. Anything that's uncountable is called a continuous random variable, okay? So let me give you a couple, and let's see if you can do those. How about your score? Let's go back to this. Your score on a 10-point quiz. Your score on a 10-point quiz. Is that going to be a discrete or a continuous random variable? Discrete, right? You get a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's see. How far you can throw a baseball. Is that discrete or continuous? Continuous, right? Because it's not just 53.0 feet, it might be 53.1963 feet. Does that make sense? Okay. So discrete versus continuous. Now, why that's important is because if we know it is discrete or countable, what we're trying to do is visualize the probabilities. Okay, we're trying to visualize the probabilities and via something called a probability distribution. And if we can count the number of things, if it's finite, we can show that through something called a probability distribution table. That's what we're going to focus on in chapter 6, is discrete probability distribution. So we're going to talk about a discrete probability distribution table. If it's not countable, that's what we're going to focus on in chapter 7, we're going to have to use functions. Okay, we'll talk about those, like a normal probability distribution function or an exponential. But we're talking about random variables today that are countable. And it kind of looks like this. Okay, this is what a discrete probability distribution table looks like. So I'll do this for, okay, I have twins. Might as well use the example. I have twins. X is the random variable I'm interested in studying, and X is the number of daughters, okay, that I have when we have twins, okay? So what are the options that can take on? What are the values X can be? If I have twins, I can have the fewest number of daughters is fewest, 0, most, 2, 1. 0, 1, and 2 are the options, so that is definitely discrete. It's countable. If I write in, this is 25%, this is 25%, and there were 2 options where I got 1 daughter. Male, female, female, male. Those were both 25%, so it's 50%. Does this make sense? Remember the tree we drew? Yes? Okay, so we can use this. Now this is a discrete probability distribution table, and we can use it. All we're doing is showing the probability. But I can use this. For example, when I talk with my wife, I said, what's the odds that we have at least 1 daughter, that X is greater than or equal to 1? How do we get that from this table? What would I do? X is greater than or equal to 1. How did I get that? Go ahead, Yolanda. Yeah, just add these two. 50% plus 25%, that gives me 75%. The odds that I have exactly 0 daughters is, just look it up, 25%. The odds that I have, I don't know, let's say, 3 or more than 2 daughters. How about the probability X is greater than 2? This makes sense, but just read the table. Probability that I get more than 2 daughters when I have twins. That can't happen, right? So that is 0 because it's not in the table. The probability that I have less than 3 daughters when I have twins, what would that be? This makes sense as well because what's the probability I get less than 3 daughters? 100%. Does this make sense? Okay. Now, this is all well and good, and I think this is pretty straightforward when we have a discrete probability distribution table, how we read this. But I want to know, okay, I want to know something else about this. I want to know an average. Okay? I want to know the average number of daughters that I would have. Now, in this case, it's going to work out. So I could probably use another example. All right. Let me change the probabilities of this. Let's say my wife and I are more likely to make boys than girls. So let's say this is actually 40%. This is 30%, and this is 30%. Okay. If I wanted to know the average number of daughters I have when we have twins, well, you might say, add up these 3 values, 0 plus 1 plus 2, that adds to 3, divide by 3, and I get 1, right? And that's what it would have been otherwise. But if we're more likely to have sons than daughters, maybe it ended up in this kind of situation. Well, let's change this to 40, this to 20, okay. So how would I figure out an average when those are the odds? Anyone have any idea? Anyone have any idea? And there's odds involved with things like this. How do I factor in the odds? All right, let's maybe this is too obtuse. Let's make a game, okay? Let me make another example. Let's say x, the probability of x, and let's make it simple. There's two outcomes. Me and you are going to make a bet. Okay, and you're either going to win $1,000 or lose 500. Okay, you're going to win 1,000 or lose 500. Okay. Now, if you wanted to figure out the average payout, right? Well, you'd add those two together. 1,000 plus negative 500 adds to 500. Divide by 2, you get 250. Okay, does it make sense? But what if I told you these are the odds? Yeah, fine. How does that change things? You probably wouldn't do it, right? Because you intuitively looked at that, Delando, and said, probably no go. If I change this around, Delando, 90%, 10%, let's play it, right? So we need to factor in the likelihood of those events. And we do that with something, let's just go back to, I don't know, let's go to, well, I'll leave it alone, 1090. We do something called, and how can I factor that in? Maybe you guys can deduce this. How do I factor in those probabilities? Any idea how I average those, so I factor those into the situation? Yes, no? Come on. You did it intuitively, Lana. You said, I'd probably go for it. I probably wouldn't go for it. What did you do, though, intuitively? You factored in both the magnitude. What if it was like this? It was 90%, 10%, but instead of winning 1,000, Delando, you could win 10 million. 90% that you lose, 10% chance you win, but the 10% chance you win, if you win, it's $10 million. Would you do that? Yeah, you do it. You might even you come to me and said, Dr. Miko, you didn't have $500. I'd say, sure, I'll back you, right? I'll take half or something like that. I'll back you. But why? What did you factor in then? Because the odds stayed the same. What did we change? Okay, so we need something that factors in both of them. And the way we do that, let me pull up the slide. And this is the most important thing in this section, is we use something called a weighted average, something better called the expected value. Okay, the expected value. And this is the formula. Well, it's ugly, but it's not so bad. The expected value of x, that's the random variable we're interested in studying, is equal to, and it's also called the mean, all the x's times the probability x's, all summed up. Okay, so for example, if I want to figure out the expected number of daughters I have in this situation, I would go through and multiply, okay, the first x, which is 0, times 40%, plus 1 times 40%, plus 2 times 20%, and I get, let's see, 40% plus 40%. That gives me 0.8 daughters is the average number of daughters I would have in this situation. If I wanted to figure out the average or expected return over here, let's see, 90% times negative 500 is negative 450, plus 10% of 10 million is 1 million. Okay, so 1 million plus a negative 450 is 999,550,000. Okay. So that is a positive expected value. So he was smart to play that game, right? He was smart to play that game. Now, if it was a little closer, okay, if this was only 1 million, only 1,000, and maybe the odds were, I don't know, let's say 60-40. We'll make it a harder decision. What do you think in this case? 60-40, 60% chance you lose 500, 40% chance you win 500. What do you do, Mr. Boyd? You chance it, okay? So let's figure out what the expected value is. 60% times negative 500 is negative 300 plus 400. It's a positive expected value. It's $100, right? It's $100. How about this? What if I change this to, I don't know, let's say 80% and 20%? Now what are you thinking? What do you say, Mr. Boyd? You're not going to play? No? Would anyone play? No? I don't know. I don't think that's that bad of a deal. It's going to have a negative expected value for sure, but let's see, 80% of 500 is negative 400. That's going to be positive 200. The expected value is negative 200. So you're saying, oh, that's why we didn't play. Do we ever do any things that have negative expected value? You never do?
Yeah.
Give me some examples of things we do that have negative expected value. What's that? Come here. Lottery, for sure. Any kind of gambling activity has negative expected value, right? The lottery, you go play slots, you go play roulette, you play blackjack. Guess what? It's a negative expected value. The odds are weighted in the casino's favor, right? So what's great is they know, and that's how expected value works. If there's enough sampling of it, overall, it's going to come out in their favor. You might win once, maybe you win twice, hell, maybe you win 2 out of 10 times, but if you play enough, right, it's 80% in their favor, it's going to come out to their avenue, right? So that's one example of where expected value is utilized. Where else?
Not studying for a test.
I'm studying for a test.
So like expecting to do well and not studying.
So you're saying like...
I mean, if you don't study, would you be like not expected to do well?
All right, so what you factor in like some kind of like if I don't study versus I study. Or how many minutes you study? I don't know what you're doing there.
I don't know. One minute that would be like another expected value.
Yeah, you're expecting not to do well, I guess, right? I'm trying. I hear what you're saying, but I'm trying to think of an entire industry that some of you may work in that is all based on expected value.
We look for positive, one that's positive or negative.
I don't care.
Maybe playing a sport, like for the odds not set out for you to win, like you were saying. So
Okay.
that's
I guess, but that's kind of like there's some that's kind of hard to say. That yeah, I see what you're saying, but will you have something there?
Would like people like the insurance agency?
That's the example I was looking for. So think about insurance, right? Who has car insurance? And we have to have it, right? So if you think about it, when you get car insurance, the place that insures you, they don't care about you, right? They really don't care about you. What do they care about you? What are they looking at from their end? Yeah, they care about, if we insure this dude, what's our expected payout for him this year, or her, right? That's what they care about. What is X? Random, how much do we have to pay out? And it goes like this. They say, 0, which was great. They don't have any claims on a year. Maybe they have, a minor fender bender. So that's, let's say, is 1,000. Let's say a major one, 10,000. And let's say, you do something really, really bad, and 300,000 is what they have to pay out. And they have odds for this, right? They may have, this is 95% of the time, we won't have to pay out anything to this person. Maybe, 3% of the time we have to pay out $1,000. Maybe, I don't know, 1.5% of the time we have to pay out 10,000, and only half of 1% do we have to pay out 300,000. So if I did my math right, I wanted that to add to what, 1 or 100%, right? So if you think about it, if I'm the insurance industry, I'm insuring a whole bunch of people like John Miko, and I figure out those odds, I want to figure out my expected loss on John Miko. So I'm going to take 0 times 95% and get 0, plus 3% of 1,000. I think you get, what, 300 there? No, 30. Plus 1.5% of 10,000. What does that give me? 150 plus 0.05 of 300,000. I think that gives me another 150. So I add those together and I have $330. Okay. So that's my expected loss on John Miko, right? That's what I expect to lose on John Miko, or pay out on John Miko. So if I'm the insurance company, what do I charge John Miko? Or people like John Miko? Do I? Exactly. I want to charge whatever my expected loss is, right? I want to charge more than that. What do they call what you pay the insurance company? Why do you think they call it a premium? Because it's a premium above what their expected loss on you is, right? So that's how they make money. So they know, think about it. They know we insure thousands of dudes like John Miko, sweater vest, Honda Odyssey driving dudes, right? And we know that these are the odds that this guy has a loss. And we know 95% of them, they'll pay us our premium, no deal. No, and we don't have to pay them anything. 3% we have to pay out 1,000, 1.5% we have to pay out 10,000, half of 1% we pay out 300,000. And if I wreck and have a $300,000 accident, they will pay, right? They will pay. And they will make money because for every one of those, there is nearly 100 others that just pay me their premium. You know what I'm saying? They're spreading the risk across a lot of people. I'll give you another example. I have term life insurance. So my term life insurance policy is it's $1 million. Like if I die, my wife gets $1 million, which someday she'd like to collect that, I'm sure. But if I die in the next 17 years, she gets $1 million, okay? So when I got that policy, I think I pay $450 a year for that policy, okay? Which isn't bad, $450 a year. But before they gave me that policy, what did they do? Yeah, they came to my house, they took blood, they weighed me, they asked me about my family history, they checked my arms for needle tracks, they asked what kind of activities I'm involved in, right? All those kind of things. They looked at my medical history. And they didn't say this, but what were they trying to figure out? That's a kind of a simple thing. Exactly. So it's a real easy discrete random variable table for them, right? There's either two options for them. I die, right, and they have to pay out $1 million, or I don't die and they get, what, $450 over 20 years, what is that, $9,000, right? So I was kind of happy that I got a low rate because they figured out that the odds of me dying, were very low, right? But if I die, they will give my wife $1 million because for every one of me, that dies, there's thousands that don't die in those 17, 20 years, right? So think about it. The insurance industry is all geared toward expected value. How about banking? How is banking geared toward expected value?
Like loan stuff.
Yeah, so how are loans geared toward expected value?
They're gonna see if you're gonna default on your loans.
All right, so why, when you have a worse credit score, you kind of think this is taking advantage. I have a lower credit score or worse credit score, I pay a higher rate. Why is that?
Because you don't think you're gonna pay that back.
Yeah, but then why, if they don't think you're going to pay it back at all, they're not even going to give you the damn loan. But if you have a bad credit score, they say, I'll give you a loan, but we're going to charge you a higher rate. Why? Why?
Make money.
Yeah, but why? You're right, to make money, that's all they care about.
You get back credit.
Yeah. But why? Why, if you have good credit score, they say, all right, we're going to give you a lesser rate. What are they trying to do? If you have bad credit score, they know the odds that you pay back is less, right? So we're going to have to charge you a higher rate because people like you, right? We know we're going to default 10% of the time. So we have to make it up on the people like you that pay back, right? So that's why that is. It's all based on expected value. Does this make sense? This is a very, very, very powerful concept. It's a simple concept, but it's a powerful concept. How about this? There's a game show. I don't think it's on anymore, but it was all based on expected value. I don't think it's on anymore. Maybe you guys remember it though.
Right?
No. Price Right's still on it. It had, do you remember Deal or No Deal?
Oh,
yeah.
Okay. So how, is that still on? So Howie Mandel, they had those models with the briefcases. I think they had 24 briefcases, 26, very good, you know. And it went from a penny to $1 million, right? And so what they started doing, think about it, the odds that your briefcase has the $1 million is 1 out of 26, right? So it's very easy. It's a discrete random variable table. 1 out of 26 that you have a penny, 1 out of 26 you have a dime, 1 out of 26 you have a buck, $10, 1,000, the whole way up. So what happens? They started knocking out possibilities, and they made it all dramatic because that's what they do. And they say, we're going to go up to the banker, and they have some black, dark figure, that's shadowed, you know what I'm talking about? And they're like, the banker is making you this offer. Well, they don't say this because it would be boring, but what is that offer based on, do you think?
It's in the briefcase.
What's in the briefcase? But now say you're down to 4 briefcases, and they're all pretty high value. That offer is going to be high. Why? Even though you might have a penny in your briefcase, they don't know what you have in your briefcase. Or maybe they do, I don't know. But they're not supposed to know what you have in your briefcase. Yeah, so what do you think they calculate to base that offer on? Right? Expected value, right? What's the expected value? And if you have all crap suitcases left, the offer is low because the expected value is low, right? You knock out some of the low ones, it goes up, right? It's all based on expected value. Does this make sense? So it is the most popular, when we're talking about probability and risk, it's the most popular decision technique. I want you to do one for me. I want you to do number 8 in your book. And here's what I want you to do. I don't know what the instructions say, but I want you to define the random variable x. What are we interested in studying? Draw the probability distribution table and figure out expected value. Number 8. Oh, a couple of things. Invest in Success is a competition Enactus runs. It's kind of like Shark Tank. You ever hear of that? So if you have a business idea, there is a form you can get from Miss Bauman downstairs in the dean's office by Dr. Fry. It's a pretty simple form. You write a paragraph about your business idea. And if you get selected, you get to present in front of a panel of judges for up to $2,000 in cash. So it doesn't have to be a real thought-out business at this time. It can just be an idea. All right. So I think the deadline's Friday. I think they're going to extend it, but Ms. Bauman has sent out many emails, so you can see the form. It's pretty simple. So I think they have very few entrants at this time, like 5. So if you submit, you're probably likely to be asked to present to a group of sharks. No, you get money though. It's better than money.
You have to spend it on the 10 points.
Yeah, they don't track that, so you can spend it on, floppy hats and like. Good. So that's investment success. The other thing, and I will give you extra credit for this, Mr. Boyd. I am the St. Francis University team captain for Movember. This is the 6th year of me doing it. We raised, over 5 years, we raised $7,500, which is nice, and a lot of money to help fight men's issues, like so men's cancer, like prostate cancer. 1 in 6 people, 1 in 6 men get prostate cancer. So we probably have about 18 men in here. 3 of us are going to get prostate cancer in your lifetime. Testicular cancer, men's mental health. So it's to help for men's fitness. So in November, there's 2 ways to participate. You can either grow. Okay, so you start November 1st, shave clean, and then grow a mustache and or beard or whatever you grow. Or women can participate as well by pledging to move, do some kind of fitness movement. So there is a page, where you can sign up. If you sign up and raise at least and do something and raise at least $10, I will give you a couple bucks, $2. All right. So November, right? It's a good cause, raises awareness. You'll see my ridiculous facial hair for the month of November. Right? That's that. The other thing, you guys are doing advising right now. I teach a class in the spring called Advanced Excel. Basically, we go into, all we do is spend time on Excel. Week to week, we spend time on Excel. So young alum, when they come back and they talk to me, they say, Dr. Rico, Excel is such a valuable skill. I'm glad I had it in your class. I wish I knew more. Well, that class we started offering 3 years ago for that purpose. So you don't have to be a genius to take Advanced Excel. Helps, but you don't have to be a genius. But it's offered Monday, Wednesday, Friday, 9 a.m. I'm the teacher of it. I'll be in this classroom. So if you'd like to take that, it's MIS 409, Section B. Okay. All right. So you guys do this one? All right, let's do number 8. It says, you've been given the choice of receiving $500 in cash or receiving a gold coin that has a face value of $100. However, the actual value of the gold coin depends on its gold content. You were told that the coin has a 40% probability of being worth $400, a 30% probability of being worth $900, and a 30% probability of being worth its face value. Basing your decision on expected value, should you choose the coin or the $500? Okay, so what is X? What are we interested in studying? What is X? What is the random variable we're interested in studying? Rachel? Yeah, the value of the coin, right? Gold content leads to that. But X, the random variable, is the value of the coin. That's what we're interested in studying. So what are the options for the coin? What's the worst case scenario? What's the lowest value it can be worth? $100, that's its face value. What's the most it can be worth? 900, and there's also an option of it being worth what, 400? So very much discrete. There's only 3 options for the coin. It has probabilities for that. 40% chance of being worth 400, 30% chance of this, and a 30% chance of being worth its face value. Notice, and I didn't go through this, but probabilities, once again, always between 0 and 1. Probabilities always add to 1. I want to know the expected value of this gold coin. I'm going to multiply all these. 100 times 30% plus 400 times 40% plus 900 times 30%. This gives me 30 plus 160 plus 270. That gives me $460. So if you have the choice of $500 or taking this gold coin, which you're not sure what it's worth, if you're using the expected value criterion, what would you do? Take the $500. Now, if you're not using, if you just want to, would anyone take the gold coin instead? Even though they knew this information, they would take the gold coin instead. I would, right? Okay. And why? You're saying, well, Dr. Miko, don't you know it's 460 is the expected value, but $500? Well, it's a one-time deal, and I also know that hey, there's a 30% chance of being worth $900, and I can you know, I can lock in at least 100, and maybe I'm a little bit of a gambler, right? So we do that all the time. There's a difference between expected value and expected utility, okay? What is utility? What is utility? Anyone ever hear utilitarian or utility? What's utility? Nothing? Go on, Google the damn thing. Look up the word for me. What is utility? What's utilitarian? What's that word base mean? Go ahead, sir.
Utilitarian creates good.
Right, okay. You're right. Utilitarian society is like, you know, everyone's happy, everything's good. What's utility mean? You Google it, Evan?
Being useful.
Yeah.
Probably.
Yeah. So utility is the usefulness or happiness that we get out of something. So think about it. You guys told me the expected value of playing the Powerball is negative, right? We know that. It's a loser. Gambling is a loser, but people do it. Why? Well, playing the Powerball only cost me $2. Does that cost me a lot of utility? It's just $2. I drop $2, no big deal. If I win, wow, that's a lot of utility, happiness. Because you start thinking about what you're going to do. I'm going to buy an island. I'm going to quit my damn job. You know, you think about that, right? You know, things are going to be. And even if you lose, you get utility out of thinking about those things, right? Like, you ever see that? People say, if I win, they get happiness just out of thinking about that outcome, right? And that's why, and think about the insurance. We say insurance is a bad deal for us people to buy, right? Because it's a negative expected value. But that, if my house burns down, that's catastrophic. That's a lot of utility loss. So I can pay $500-600 a year. That hurts me. But this is catastrophic for me, right? So utility and value or payoff are two different concepts, yes? If not, we would never buy insurance. We would never gamble, right? One thing you would do is you would be here. Why? Why are you here? Why are you here? Jonathan, you have smiley eyes, Jonathan. You look at me and I'm like, all right, I want to hear what Jonathan has to say.
Why am I here?
Yeah, why are you here? I can't wait to hear this.
So I can take that quiz this morning.
All right, you had to take this quiz. But why are you at St. Francis University? Why are you an undergraduate student here, Jonathan? Why did you decide I'm going to get a 4-year degree? Don't say to play soccer, Jonathan.
It'd be easier to get a job eventually.
Okay. So if you think about it, you know, there are a lot of things. There are a lot of factors. Like the likelihood that you live in poverty goes down. So if we look at lifetime earnings, these are averages, right? But lifetime earnings, if you just have a high school degree, it's about $1 million. If you have a 4-year degree, it goes up to about 1.9. Those are averages. You still might live in poverty, Jonathan, right? But you might make a hell of a lot more than $2 million as well, right? So what you've done is you've made a calculated, you know, you said, I'm going to increase the odds of these things occurring to me, right? You've changed your table. You have. You know, by getting a 4-year degree, you change your table. You do. You increase the odds of being wealthy, the odds of all those good things occurring, all right? And by the way, think about car insurance. I know we're running late here, but car insurance, no, we're not. Car insurance. You guys, I feel bad for you guys. My 16-year-old, my car insurance went from, with me and my wife and 2 cars, went from $900 a year. Now my 16-year-old son, we got a 3rd car, and we put him on 3rd car. Guess what I pay a year now? $2,600 a year. It went up, tripled. Why? Lucas is a pretty good driver. I mean, he's a 16-year-old boy, so he's kind of an idiot. But no, he is. But he's a pretty good driver. He really is. So why do I pay $2,600? Because of Lucas, but because of 16-year-old boys. They know that they have more accidents because they're 16-year-old boys, right? So the insurance company says, hey, we need to get this money back because likely this kid's going to wreck his car, right? There's the odds of him wrecking car go up. Yes.
Like what age does that start going down?
I think it's like 20, it depends who your cover insurance
It's
is.
just now, depending on the years that you don't have an accident. So if you go by 2 years without having an accident, and all
Yeah.
It's still gonna be high at 18, even if you
Yeah.
hadn't an
And it goes
accident.
down.
It'll go down. 25 is like, you know, kind of like a magic point, when they start letting you rent rental cars, like, you know, 23. I can tell you, I had 3 accidents before I was 18. Yeah, I was a 16-year-old idiot, right, 17-year-old idiot. I wrecked my dad's Aerostar van a couple times. So, here's what I'd like you to do for homework. One and two are just like conceptual, just do those. 1 and 2. 3, 4, skip 5. Do 6 and 9. We did 8 already. All right, I will see you guys on Tuesday. Good luck to all the sports teams competing. Have a great weekend. Happy Halloween, all that good stuff. It is Monday. It's October has gone fast.
We're gonna do your homework.